So let's start where we finished yesterday. So we didn't quite finish the second part of lecture 1 on logarithmic barriers for sparse matrix cones. And I forgot to mention this is from a paper with Mark Anderson, who's a PhD student at UCLA, and Joachim Dahl, who's a postdoc, and now at Mosec. And we also have a software package with the implementations of all these methods. So we're discussing two matrix cones defined or associated with a symmetric sparsity pattern. A cone of symmetric positive semi-definite matrices with that sparsity pattern, and then a cone of the matrices, sparse matrices that have a positive semi-definite completion. And those two cones are dual cones. And we'll use this in the next part in interior point methods for conic optimization. So we need to know barrier functions for these two cones and have efficient methods for computing, evaluating the functions and their derivatives, or at least the gradient and the Hessian. So for the first cone, a cone of positive semi-definite matrices with fixed sparsity pattern E, we use the standard log-dead barrier, but restricted to the subspace of matrices with that sparsity pattern. And we can evaluate this easily by taking Cholesky factorization for given x, and then from the diagonal of the Cholesky factors you get the log of the determinant of x. So that's an efficient method for computing the barrier. And then by the chain rule, it is to be expected that if you can efficiently compute the barrier by Cholesky factorization, you should be able to also compute the gradient and the Hessian and the derivatives efficiently. So the gradient of the log-dead barrier is given by this expression. It's the projection of the negative inverse of x on the sparsity pattern. So if you have a large sparse matrix and you want to compute this gradient of this function, then you have to compute the entries in the inverse in the positions of the non-zeros in the pattern. And you don't want to compute the entire inverse because that would be much more expensive if it's a large sparse problem. For example, for a banded pattern, the question is how to compute the values of the inverse of a sparse banded matrix on the main diagonals of the inverse. And you're not interested in the other entries of the inverse.
Maybe you should remind people that when we calculate gradient, we have in mind that the norm is given by Frobenius norm.
So for matrices, I always assume we use the trace inner product. So the inner product of x and y is trace of x times y. And this is exactly, and we use that same inner product also for the space or for the sparse matrices, and for that inner product it is so the Hessian is then defined as a title here yesterday. So in interior point methods you also have to be able to apply the Hessian to a given matrix or given vector. So and this expression stands for the derivative of the directional derivative of the gradient in the direction y at t is 0. And the expression is this. So if you take a full set of full matrices, this would be the expression for the Hessian. So here again you have to project it on that sparsity pattern. And here the question is for a given sparse matrix y, for example band matrix, and a given positive definite sparse matrix x, evaluate this expression without actually computing this entire dense matrix or the entire inverse. So if you can do this, then you can implement a barrier method for conic optimization problem with this cone efficiently. So for the dual cone, we'll so if you take this as the barrier function for the first cone, and for the dual cone, the standard choice is the dual barrier, which is defined as the Legendre transform of the negative of S. So it's defined like this: for a given S in the interior of this dual cone, in this case the positive semi-definite completable matrices, you evaluate the barrier by solving this optimization problem. So this is the inner product of S and X, and this is the negative of the barrier. And the value is the value of the dual barrier function at S. So in general, you will have to solve this by an unconstrained optimization problem. the optimal x satisfies this, so the gradient of phi is equal to minus s, so that's this optimality condition. So solving this problem actually involves solving this nonlinear equation. You're looking for a sparse positive definite matrix x hat that satisfies this nonlinear equation. For given s, the projection of x inverse is given and has to be equal to s. So that's the general nonlinear equation, and it's the gradient condition for this optimization problem. And you can also show by duality that the dual of this problem is actually a maximum determinant positive definite completion problem. So in this, so that's a very classical problem in linear algebra. So you're given a sparse matrix S, and you're trying to find the completion of S that has a maximum determinant. So the matrix with maximum determinant that has a projection equal to S. And the relation between these two is that at the optimum, Z is the inverse of x hat. But it's more useful to look for x hat than to Z, for Z, because Z in general will be completely dense, because it's the maximum determinant positive definite completion, will be completely dense. But the inverse of Z will be sparse. So that's much easier to handle and to compute. So this arises in also many other applications of this problem, also in graphical models and statistics as maximum likelihood estimation of graphical models for Gaussian variables. So that's the value of the dual barrier. Then from convex analysis we know that if this is the definition of the function and x hat is the maximizer in the definition, then x hat or minus x hat is the gradient of phi star at S. So we get that by the same calculation. And then the Hessian of this is, again by convex analysis, the inverse of the primal Hessian at that optimizing x hat. So the problem of evaluating the inverse is actually the same as evaluating the inverse of this primal Hessian. So for a given value of this, you have to solve for y. To solve this system, instead of just evaluating this, applying the Hessian to y, you have to solve the inverse. So those are the expressions for the barriers and their derivatives, and here I didn't assume anything about the sparsity pattern E. So then it turns out, so the main point of the rest of this section is that for a Chordal sparsity pattern, all these questions are very easy, and you can calculate all these quantities at a cost of roughly the same as a Cholesky factorization. So there are finite methods that follow from a similar recursion as a Cholesky factorization, and you don't have to, in this dual case for example, you don't have to solve this numerically, you can solve this problem just by something that looks very much like a Cholesky factorization. So that's what we'll do in the next few slides. So just to remind you of some of the notations and definitions from yesterday. So from now on, I'll assume that E, the sparsity pattern, is Chordal, and for simplicity, assume it's the ordering we use is just a natural ordering. So for this natural ordering, that's a perfect elimination ordering. And then if you represent the sparsity pattern or the graph by an array like this, or you can think of this as the sparsity pattern of the half of the symmetric matrix. So you will have a non-zero in the position of the dots, and the rest will all be zero. Then we used yesterday these notations for the graph, so the monotone adjacency set of a vertex and the closed monotone adjacency set. So here they just refer to the columns, non-zeros in each column. So for column J, this set is just the indices, row indices of the non-zeros in column J. Here for simplicity we call that gamma J instead of cog J. And then the monotone or higher neighborhood is the same set but without the diagonal. So for example, for column 2, gamma 2 will be 2, 5, 7, 8, so that's the structure of column 2 of the sparsity pattern. Eta 2 is the same but without the leading 2. And then all the algorithms will be formulated in terms of an elimination tree. And the elimination tree was defined from the pattern like this. So the parent of a vertex, each vertex corresponds to a column or a row. The parent of a vertex is the row index of the first lower triangular element in that column. And then the important property of a Chordal structure is that you have some restrictions on this triangular pattern. It's not an arbitrary lower triangular sparse matrix, but it has to be filled or monotone transitive. And in terms of this notation, it means that for every column, the non-zeros in that column must also be non-zeros in the column that corresponds to the parent. So these three non-zeros must also be non-zero in column 2, because 2 is the parent of 1. So in this notation, it means that eta, this lower, strict lower triangular part of the column, must also be a subset of the column in the parent. And that's the important property of Chordal matrices or filled sparsity patterns, and that's what we explore. So the basis of the algorithms that we discuss is a very classical method for sparse Cholesky factorization. It's called the multifrontal method. It was invented in the 1980s. And I'll skip the details, but it computes a factorization of the positive definite sparse matrix X. And here I use this, L is lower triangular with 1s on the diagonal, and D is positive diagonal. And it's for a Chordal matrix, so we know L and X will have the same sparsity pattern. So the important features of this method are that it follows by a recursion on the elimination tree. So you start at the leaves of the elimination tree, and then you go through the tree in a topological order. So you visit every parent after its children in a topological order. And in this method, you associate with every vertex in the tree a dense matrix that's called the update matrix. And the update matrix is just a subset of this Cholesky factorization. So you take a sum of outer products, but you sum only over the descendants of vertex I in the elimination tree. And a part of the, so each of these terms is dkk times a part of column k of L and its transpose. And in column k, you only take the subvector that with row indices that correspond to the non-zeros in column I. And we know from this last property that that certainly includes all the non-zeros in column k. So this is a dense submatrix, and you associate one of these update matrices with every vertex in the elimination tree. And we don't really need to store it, we only need it as an auxiliary variable when we pass through that vertex during the factorization. So that's the update matrix, and if you define this update matrix, then you can write an equation that allows you to easily solve the computer Cholesky factorization column by column. So it looks complicated because of the indexing, but if you look at a certain column J, so xjj is the diagonal of the matrix that you're factoring. This is the non-zero part of column J in X. This is the rest of the row. This is the column J of the Cholesky factorization and the diagonal. And the other terms that it is an equality involve the update matrices at J, the node at the column that you're factoring, and then the update matrices of the children of J at the in the vertex in the elimination tree. So you have this equation that is basically this, but using this notation for update matrices. So then if you look at this carefully, you see that if you process the vertices in topological order, so you assume that when you arrive at vertex J, you've finished the factorization of all its children, then, and you know the update matrices for the children, then you can compute this matrix. And actually these matrices P, eta I, and gamma J are needed because these update matrices refer to different indices in rows and columns. So basically here, these operations just copy the update matrices of the children of vertex J to the correct position in this submatrix, because they refer to different indices in the n by n original matrix. And we do that actually by copying first to n by n matrix in the correct position, and then from that matrix we extract this subnet. But the notation gets a little complicated because of indexing. But that doesn't really matter because this is a matrix that you can compute if you know the update matrices of the children of J. Then you also know from X this part of row column J and row J. And then from this you can see that you can, from the first column, you can get the column J of the factorization of L. And then also the update matrix, the new update matrix for vertex J. So anyway, in the outline of the algorithm that looks like this, you process the vertices in topological order, so starting at the leaves in any order, but you also always visit the parent after finishing all the children. Then at vertex J you have to compute what's called a frontal matrix, and it's a part of column J and row J of the matrix that you're factoring, plus a combination of all the update matrices of the children. And then you do one pivoting step to get column J of the factorization, and a new update matrix for vertex J. And then you finish with vertex J, and then you can actually delete the update matrices for its children because you don't need them anymore. So at each iteration you do a column of the factorization, and you get a new update matrix that allows that then you pass through the parents of the parent at vertex. So that's the multifrontal algorithm. It's so it uses the elimination tree, and it breaks up the Cholesky factorization of a sparse matrix in basic operations that involve dense, smaller dense submatrices. So in this case, this is the main matrix vector operation, this dense outer product. And part of this you can do in parallel, of course, because different branches of this tree can process in parallel. So that's a well-known method for multifrontal, for Cholesky factorization. And then we'll do, there are similar methods for the other questions that we're interested in, computing the gradient of the barrier, and the dual gradient, and the Hessian, and so on. So first, the gradient we've seen is actually the partial of the projected inverse of x. Suppose we've computed the Cholesky factorization, and then we're interested in computing the entries in x inverse in the positions of the non-zeros of x. So if you write the inverse of the matrix in terms of the Cholesky factorization, you get this equation for S, and S is the inverse of x, the full inverse of x. And then if you look closely at this equation, and this would be an example actually for this elimination tree. So suppose this is a 9 by 9 matrix. The filled circles are the non-zero positions in x. This matrix represents the inverse of x, so everything is non-zero in principle. But we're interested in computing only these entries in x without computing the other entries. So if this is x inverse, and we write this equation, S times L is L minus T times the inverse, for column, in this case, column 5. So column 5 of L is a column of a unit lower triangular matrix. So it has a 1 on the diagonal, and then non-zeros in these positions, eta, what we call eta j. Because that's by definition would be just the non-zeros positions of the column j. The right-hand side of this, column j of the right-hand side, is the inverse of transpose of L times the diagonal matrix. So the transpose of the inverse of L will be upper triangular with a 1 on the diagonal, because L is a unit triangular. So this will have some entries above the diagonal, and then the inverse of d5 on that position. And then if you look carefully to the block that you associate with vertex 5, so the diagonal, plus the non-zeros in that column and the non-zeros in that row, you get an equation like this. So Sjj is the diagonal, then you have the non-zeros in that column, non-zeros in that row, and then a full block in the 2-2 position. But if you write this equation, you see that if you look at only these three equations in this equation, then you see that you can evaluate the diagonal in the first column in the row from, if you know this block. Then you can easily solve for Sjj and S eta j. If you know this block, then you know L and D. So that means if we go through this elimination tree in an inverse topological order, so we start at the root and then visit every vertex after its parent, then when we complete the entries that we're interested in this matrix S, then when we get to vertex J, we'll know this block. because those are non-zeros that are associated with ancestors of columns that are ancestors of vertex J. So if you do it in a topological order, then you know this block when you arrive at vertex J, and then you can easily compute these red entries. And then you can move to the next vertex in its inverse topological order. So you get something that looks very much like the multifrontal method, except that you use a reverse topological order. And this block plays the role of an update matrix that you pass from parents to children. And it allows you to actually compute all these entries of the matrix that you're interested in, and none of the other entries that are outside the sparsity pattern. So this is the outline of the algorithm, so the details already matter, but at vertex J, you use this system to solve for the first column of S, so the diagonal and the non-zero part of the rest of the column. We assume we know L and D because we first did the Cholesky factorization, and we know this matrix because that's associated with one of the ancestors. Those elements are associated with ancestors in the tree. So you can solve for the first column, and then you compute from the part of S that you have to pass to the children to get this new update matrix. So this portion, 2 by 2 portion, plays the role of an update matrix that you pass from parents to children in this case. So you get something that looks more or less dual to the multifrontal Cholesky factorization. Again, you break everything down to dense matrix vector operations. In this case, it's this matrix vector product is the main step. So that's the projected gradient, and that's useful for the primal barrier function. So the dual barrier function that we see actually requires you to do the inverse. So the primal barrier was for a given x, compute S, the projected inverse. For the dual barrier, in this conjugate dual, we had to actually solve this equation. So for a given S that has a positive definite completion, you're trying to find a matrix X that satisfies this equation, and that's the right sparsity. Well, you can, so this solution, this matrix solution of this will be the inverse of the maximum determinant completion. It's also our dual gradient. And so you can actually compute this by looking at the same equation that we used for the primal barrier, except that now we assume that S is given, because that's the right-hand side of this equation. And then we're looking for L and D. So given S, we solve for L and D, the Cholesky factors for the solution X of this equation. And you can do this in a similar way, so you just look at the same equation, except that now S is given, and you solve for the Cholesky factors. And you get an algorithm that looks like the first gradient algorithm. You just, again, you have a recursion over the elimination tree in inverse topological order, and you have something similar. The one difference here is in the first step, for the primal gradient, we have a matrix vector product. Here we have to solve an equation, so it's slightly more expensive than just a matrix vector product. But you can improve this by exploiting the fact that these matrices V, so these update matrices, are related. So if you propagate instead of V a factorization of V, you can actually make this almost as inexpensive as in the primal gradient. So these are two examples for very simple chordal patterns. So band pattern is a chordal sparsity pattern. Also an arrow pattern is a chordal sparsity pattern because they have zero fill Cholesky factorizations. And the point of this plot is here we keep a fixed size n, and in both cases we have a parameter w that defines the width of the pattern. And we look at the cost of computing these gradients versus w, and it confirms that the cost is quadratic in w. So we can, and that's nw squared will be roughly the cost of a Cholesky factorization of matrices of this type. This is an experiment with more realistic sparsity patterns. So we took a set of sparsity patterns from the benchmark collection. They're not chordal. The sizes range from 500 to 200,000. And this gives a scalar plot of the dimension versus the density as percentage of non-zeros, and n versus the number of non-zeros. So that's the 128 matrices. And then we obtain Chordal patterns by just doing a triangularization or a symbolic factorization of these sparse patterns. And that's actually the resulting sparse. So this shows the cost, or compares the cost of these gradients for the barrier functions with the Cholesky factorization. So on the x-axis we have the cost, the time to compute the Cholesky factorization. This is for the primal gradient, or the projected inverse. This is for the dual gradient. And you see it's almost identical, so you can do the primal gradient almost as quickly as a Cholesky factorization for that sparse matrix. And the dual gradient also, that's also true for the dual gradient if you actually use this improved version to address this problem with the inverse in the matrix. So that's the difference between these two, the red and the black plots. So that's for the two gradients, the primal and the dual barrier. Then we skip the details of the Hessian and the inverse Hessian, but conceptually it's actually very straightforward if you think about how the gradients are computed. For example, to compute the gradient of this log depth barrier, we needed two passes through the elimination tree. So first, for a given x, we compute the Cholesky factorization by an iteration in topological order. And then from L and D, we computed the partial inverse by an iteration in inverse topological order. So you get these two nonlinear recursions on this tree. So by the chain rule, to evaluate the Hessian in a certain direction, of the directional derivative of the gradient in a certain direction, you just have to linearize these two recursions at every step. And you get an algorithm for the Hessian that actually proceeds in the same way. You have an iteration in topological order and reverse topological order, and the computations are just linearized versions of these two in each step, just by the chain rule. It's interesting also to know that if you do this, then these two recursions, these linearized recursions, are actually adjoints, complete adjoint operations. So you actually also have a way, if you finish after one of the two, you actually evaluated some kind of factorization of the Hessian. So that's very useful in algorithms, because for example, in an interior point method, this is an operation that's very important. You have to, for a set of matrices AI, you have to compute a matrix with this ij entry. So you apply the Hessian to aj, and then take the inner product with AI. So if you have a factored version, you can do that more simply, because you can write it as an inner product of AI. The result of this factored Hessian applied to AI, and the inner product of that matrix with the factored Hessian applied to aj. So you can do these factorizations and then take the inner products. And that's faster and or more stable than the computing it using this method. So and this is the cost of the Hessian, and there's further savings you can do if the argument y at which you apply the Hessian is sparse, because then you can start at you can skip some computations. So this is yield the time in seconds to evaluate the Hessian. And then the final point about this for this section is we talked yesterday about supernodal versions or supernodes and cliques in the graph. So they are used in sparse matrix theory, because often you can take a scalar or a nodal version of an algorithm, like this multifrontal Cholesky factorization, and then process columns in a supernode, what we call a supernode and a supernode partition, together as a block column in the matrix. And then you can formulate methods that are very similar to the scalar or the nodal version of the multi-frontal method, but they process block columns together, so they're more efficient, because matrix vector operations are replaced by matrix-matrix operations, and also because the elimination tree is replaced by a supernodal elimination tree which has fewer vertices. So you have fewer steps in the algorithm. So this is again for a supernodal version versus the scalar nodal version for a Cholesky factorization, you have this scale, and then for the projected gradient. So that finishes that part of the lecture. So the next, we probably won't get through the entire the 3 chapters or 3 sections. So in the 3 topics that are left now in lecture 2, there are 3 applications of these Chordal techniques to semi-definite programming. So the first one is just to use these 2 barrier functions that we've seen on these 2 sparse matrix cones in interior point methods. And this was actually is from this paper, again, Martin. So if you go back to the general, sort of a few comments on conic linear optimization in general. So conic linear optimization is defined like this, as you know. So it looks like an LP, except that you replace the non-negative orthant with a proper cone, so a convex non-polyhedral cone. And that's widely used in convex optimization, certainly after the book by Nesterov and Mirovsky, because they use this framework to show that the interior point methods for linear programming could be extended to general nonlinear convex optimization, because this actually covers all of nonlinear convex optimization. And then they explain how to construct path following methods and potential reduction methods for these types of problems. So it's a very convenient vehicle for extending interior point methods from linear programming. And it's also useful for modeling, for packages like CVX or NumMap, because it turns out that a small number of cones, actually only 3 cones, are sufficient to model most convex optimization problems you encounter in practice, which is surprising. And they are the non-negative orthant, so that covers linear inequalities and linear programming, the second order cone, and the positive semi-definite cone. So CVX, for example, will always convert any problem to constraints that involve these 3 types. And these cones are not just self-dual, but they're also symmetric or self-scale, and that's an additional property that can be exploited in interior point methods to derive actually completely symmetric primal dual methods that are similar to the symmetric primal dual methods for linear programming. So that's another added motivation for restricting solvers to these 3 cones. They're actually the only symmetric cones of interest. So they're sufficient for most purposes. There are very few problems that you cannot express as semi-definite programming problems. And also they have nice theoretical properties because you can formulate symmetric primal dual methods. But the problem with this organization is that there are large gaps in the complexity between these 2 cones. Not the iteration complexity, the linear algebra complexity per iteration. And a small experiment, or 2 experiments to show this, is first if you look at an SDP. We take an SDP with a band structure and a small band, for example, tridiagonal or so it's an SDP, and the coefficients C and AI are all band matrices with a half bandwidth W. And now we look at the complexity just as an experiment. And this is from a paper, as I mentioned, from 2010, so some of these solvers might have improved since then. But this was an experiment that we did at that time. So we fix W, in this case 5. We take n a fixed number of equality constraints, and we look at the complexity of solving a band SDP as a function of n. And then you see for all these solvers, the cost is at least n squared, with the cost the size of it. And that's, I think, surprising, at least if you don't know how these methods work, because we know in the special case where W is 0, if you have a diagonal coefficients, and it's an LP, then we know the cost is linear in n. Cost of solving LP as a function of the variables, if everything else is fixed.
Could you please say a little bit about the solvers? Not everybody knows solvers.
Yeah, so there's general purpose solvers for SDP. So SDP-T3 and Sidumi are very widely used. I think, for example, in CDX you have a choice. One of these 2 is the default, you can easily change them. So they're general implementations of primal dual symmetric interior point methods for problems that involve these 3 cones. So SDP-T3 and Sidumi are very widely used and the most widely used general purpose solvers for SDP. SDP-AC, actually the C stands for conversion, or Chordal, I think for conversion, was actually a method that exploits some of the, algorithm that exploits some of the techniques that we've discussed by the group of Kojima. And then DSDP is another solver by UA and Ransom. And it's a dual variable, which is interesting for sparse methods because it's easier to exploit sparsity in dual. So they're just general purpose solvers for SDP. And the surprising thing is that it's n squared because you would expect that solving a tridiagonal SDP with a small bandwidth shouldn't be much harder than solving a diagonal SDP. But it's not the case, at least not empirically. So that tells you something about the gap between the LP case and positive semi-definite case. That there's a large gap if you just go from diagonal to tridiagonal because of a big increase in cost. You can say something similar between second order cone and SDP. And as an example, we can look at the matrix norm minimization problem. So we take a rectangular matrix F of size P times Q, and it's a linear function of the variables X, and we want to minimize the matrix norm of F of X, the maximum single value norm. So in the special case where Q is 1, it's just the Euclidean norm and it's a least squares problem. So that's very easy. If you have some additional constraints, you can handle it via second order cone program. The dual of this would be a problem like this. So you have a problem that involves the trace norm, or the nuclear norm, or the sum of singular values of a matrix variable Z, and linear objectives of constraints. So if you take this problem, the dual in the SDP form, to get the standard form SDP, you can do that by introducing the matrix variable X would have, this form would be a block matrix, and the 2, 1 or 1, 2 block is the matrix variable Z in the original dual problem. And the rest we call U and V, just a big matrix X. You have equality constraints, for example, with this matrix AI and C. So for example, for this choice of C and this choice of X, trace CX's is 2 times this objective. So you get this large problem. And so in this formulation, you can think of this as a completion problem, because the real variable is Z, and if you assume that, so Z has dimension P times Q, if you assume that Q is less than P, much less than P, then this has, if you set U equal to 0, has an arrow structure. You have a diagonal, or if you set off diagonal elements of U equal to 0, then you have an arrow. Or in other words, the values of this matrix that are involved in the constraints are only the diagonal because of the trace, and then the entries in Z. It doesn't involve any other off-diagonal entries of U and V. So it's an example of, in this dual problem, in the primal you would have a sparse matrix with this kind of arrow pattern. So this is an example where we took actually a matrix norm problem, actually added constraints to make it more interesting, least squares version. And we do something similar. If you take a problem like this and give it to CVX, so CVX may or may not use this formulation, could also take something different. But if you just take this problem and give it to CVX, it will keep P fixed, Q fixed, and increase P, and the number of variables in. Then you get a similar observation as we had before. For Q is 1, this can be formulated as in terms of second order problems, and the cost is linear in P, if you keep all the other dimensions fixed. If you take Q, as soon as Q goes to 2 or 3, then the cost becomes at least quadratic in P. And again, that's a little disappointing because you would think that solving a matrix norm minimization problem for a matrix with only a few columns wouldn't be much harder than solving the least squares problem. But it is actually more expensive because you do have to embed it in an SDP, this SDP or something similar, and there's a large gap in complexity between second order cone and semi-definite cone. So that motivates this work on non-symmetric solvers. So one possible answer to improve this situation is to allow more than these 3 cones. To large gaps between these cones, so we can just add more types of cones. For example, banded positive semi-definite cone, or positive semi-definite cone with an arrow pattern, and so on. So that's what we do now in the rest of this part. So we'll formulate the SDP as a problem with a non-symmetric matrix cone constraint. So we look at an SDP, we assume that C and AI are all very sparse matrices, and E is the aggregate sparsity pattern of AI and C. So it's the union of the sparsity patterns of AI and C. So the edges in the pattern are in positions where at least one of these matrices has a non-zero. So then if you look at the problem, you can see that the only variables in X that are important for the objective and the constraints are those values in positions of non-zeros in E. But you need X to be the only the rest of X is only needed to make it positive semi-definite. So you can formulate this problem instead of formulating it as a problem of the full cone of positive semi-definite matrices. Take the cone of matrices of sparsity pattern E that have a positive semi-definite completion. If X is in this set, it's sparse but has a completion, then you don't have to worry about the other entries. Because you know they exist, and all you need to know to solve the problem, to evaluate the other constraints, is know that there exists an X that makes this positive semi-definite. So the advantage is now we work in a much lower dimensional space for X. For example, in a banded sparsity case, X is no longer a full symmetric matrix, but a band matrix. So it's much lower dimensional. And if you take this, it's equivalent to the original SDP. For the dual, you get something similar for the dual conic LP, but the cone is the dual cone of K. So in our case, we've seen that's the cone of positive semi-definite matrices with that pattern. So you can actually solve the problem as a pair of conic linear optimization problems, but with a pair of not self-dual and non-symmetric cones. Positive semi-definite completable cone and positive semi-definite. And this is an approach that has been studied for some time. It was first proposed by Fukuda and others in 2000, and then there have been several papers on this. So the question is, can we actually do it? What do we need to do to actually implement an interior point method for this pair of cones? Well, from the theory of interior point methods, we know we have to be able to, we won't be able to solve this with a symmetric primal dual method. You can still use a primal barrier method or a dual barrier method. And we have to be able to evaluate these barrier functions for the two cones, the primal or dual, and their gradient and Hessian. If you can do that efficiently, then you can implement a barrier method for this problem. So that's what we seen in the previous part. So if the pattern is chordal, and that's why chordal patterns are useful, we've seen that you can actually evaluate all these quantities very efficiently, the barrier functions and their gradient and Hessian. For a general pattern, it might be difficult. Now, in our case, we can always assume the aggregate pattern is chordal, because you can add extra edges in E to make it into a chordal pattern. So that's a chordal embedding. So you can always take entries that are actually zero in the original pattern and consider or treat them as non-zeros, and then you have a larger graph with more edges, but you can try to embed your actual E in chordal pattern and still have an equivalent problem. So I'll skip the details of or even high-level description of the path following methods. But you know they're based on following the central path, so you have the primal feasibility, dual feasibility conditions, and then a gradient condition that characterizes the central path. And interior point methods all try to follow the central path in the different methods, and they do it by linearizing the central path equations. And then depending on how you write the nonlinear equation, you get different methods, primal or dual. If you linearize this, you get a set of linear equations for the search directions. If you first rewrite this by, in terms of the other barrier, in an equivalent form, you get a different linearization. So at each step you have to solve a big system of equations for the search directions. And delta x and delta s, in this case now, are sparse matrices with our sparse type E. And then the main step in an interior point method is actually solving for those search directions. And a barrier method, that means forming and solving the Newton system of the barrier. And actually forming the Newton system is actually often more expensive than solving it. So in this case, in this notation, if you want to find the Newton system that you have to solve at each equation, it's an equation of this form, and you have to, with h, define them this way or this way, depending on whether you use the dual or the primal method. But that's where we can use these fast methods for evaluating the Hessian of the barrier function. Because for all the coefficient matrices, you have to evaluate these products, so you have to apply the Hessian to Aj and then take the end product with Ai, and that's the Ij entry of H. So you can use these Chordal methods to form this Newton system fast, and faster than the full SDP method. At the end, you still have a dense system H to solve, because in general this will be dense, and you have to do it by Cholesky factorization. But you save on an expensive step in an interior point method, because often the most expensive, or very expensive, and sometimes the most expensive step is actually constructing this Newton system with the Hessian matrix, or the Schur complement system, rather than actually solving it. So we implemented this, and we'll test it or show some results on for the primal and dual, or we implemented it for primal and dual methods. We constructed actually two methods for solving a Newton system. One actually a Cholesky factorization. The other one solves this system by QR factorization, using this factor expression that I described. That's important. But that's a little more stable and actually more recommended, if possible, in interior point methods. So first on some Chordal patterns. We've seen band patterns are Chordal. So here these two are the two versions of this Chordal non-symmetric method. These are some of the solvers that I showed before, plus some others. So you see in this case you get the linear increase in N, complexity per iteration, as expected, and for other methods it's higher in square or more. So here, as expected, for a band SDP you get a complexity per iteration that's linear in N, if you keep the other parameters fixed. This is for a matrix mode problem, again the same observation. Then we looked at some general sparsity patterns, some Chordal sparsity patterns from this benchmark. So we took a bunch of test problems. These are not Chordal patterns, so we triangularized them by first applying a field-reducing ordering and then doing triangularization or symbolic factorization. And these are two heuristics for doing this triangularization step. As I mentioned yesterday, so AMD is a standard method. It's approximate minimum degree ordering of a sparse matrix. This is the variant of AMD implemented in the Chordal package, and it's interesting to compare them, because it's not just the sparsity or the fill-in in the pattern that matters and determines the complexity, but also the size of the cliques, and there's other parameters that actually describe the. So sometimes a less sparse embedding is more efficient than the sparse one. And then the construct SDPs, we just took random data with these sparse patterns. So these are some smaller examples from this set. So this is the original sparsity in these four matrices. This is a sparsity with the AMD embedding, so it's times 4 or 6. And this is with the Chordal embedding, which is denser, but we'll see actually works better because it has smaller, fewer but larger cliques in the graph. And these are some larger problems up to 30,000, and we have the same difference. So these are some results. So the table shows average time per iteration for different methods. So M1 and M1 are this Chordal non-symmetric method. The first one is with the AMD embedding. This is with the other embedding. So you see the second embedding was actually denser, but is slightly more efficient than the first one. So it does quite well compared to most other methods. The best method of all these general purpose solvers is on these problems is DSDP, and that is a dual method that exploits rank 1 structure in the coefficients. And it works very well on these problems because if you make problems very sparse, then often there are also the coefficients of rank 1, because there's only a few non-zero entries in the coefficients, and they are also, you can exploit that with a very different method by taking advantage of the rank 1 structure instead of sparsely. And then for larger problems, these were the only two that actually managed to solve the problems. So that's the third part of the lecture. So we used the key was to use this non-symmetric formulation of an SDP. So instead, we're looking at a conic LP that involves these two sparse matrix cones for Chordal sparsely problems. And by doing this, you can reduce the dimension of the space that you're optimizing in and save in the part of the computation in the tier point method, because you can construct the Hessian of the barrier functions fast. But at the end, you still have to solve a dense linear system, and that's still the same as in other methods. So then the next part is to use similar ideas that we discussed, some properties that we discussed yesterday for decomposition. And this is based on another paper. So first actually to relate it to what we did yesterday. So if you look at this non-symmetric formulation of the SDP that I just discussed, so then in this non-symmetric formulation we take x, and x is now, we take for x the conic constraint on x is that x has a positive semidefinite completion. And then yesterday we've seen this famous result for completion of Chordal matrices. So a matrix with a Chordal sparsely pattern E has a positive semidefinite completion if and only if all the fully specified principal submatrices are positive semidefinite. And that's equivalent. So that means that you can actually characterize this cone by adding lists of smaller dense positive semidefinite constraints. It says that each of these positive submatrices of the matrix X has to be positive semidefinite. So that's an example of a more general type of structure that we call partial separability. So here we go back to a general conic LP with a vector variable, and we say the cone C is partially separable if it can be, or it's defined like this. So X is in the cone if certain given subvectors of X are in some given cone CK. So you take subvectors of X indexed by different overlapping index sets, and then for each of these subvectors you impose a condition that it is in cone CK. So if all these, so an example would be this: you take a vector in R6, you have 4 cones, and then you say that different subvectors of X must be in each of these cones. So for example, X1, X2, X6 must be in C1, X2, X5, X6 in C2, and so on. And that's the definition of a cone in R6. And this, in this case, you would take 1, 2, 6 as a first subvector index set, and so on. So if these actually are disjoint, if it's a partition of X, then it means it's just a separable cone. It's equivalent to independent constraints on different independent subvectors. But that's not what we assume here. Here we assume that the subvectors can overlap, so that's why we call it partial separability. So different overlapping subvectors of X must be satisfied certain conic inequalities. And we call that partial separability. So partial separability is a term that exists in nonlinear optimization for functions. So a function is partially separable of function of x if it can be written as a sum of functions on subvectors of x. That's called partially separable function. So here we call that a partially separable cone because the indicator function of a cone defined like this is partially separable. And here I use the same notation as before for extracting a subvector from X using this selector matrix B. So this is an example. So the dual cone can be defined like this. It can be defined in terms of the dual cones of these smaller cones. So to construct a general vector in the dual cone of C, we take vectors in each of the dual cones of the cone CK, and then we copy them to vectors of dimension 6 in those positions, 1, 2, 6 for the first one, 2, 5, 6, and so on, and then add them. So for decomposition, this is useful because, or it should be useful to exploit this structure, because what we're doing here is we're writing a complicated cone C as an intersection of simple cones, lower dimensional cones CK. And that's a useful property, not just for the tier point methods, but also for first order methods. If you want to solve over a set C and it's described as an intersection of simple sets, for example, sets on which it's easy to project a vector. So as in the first part, you can describe the structure by different graphs. For example, you could define a sparsity graph that takes the variables x in the, so in our example was 6, and then adds an edge if two variables appear in the same index set. Or you can define it by what we call here an intersection graph. So here the vertices are the index sets, and they're joined by an edge if they intersect. And Chordal structure is of importance for the sparsity graph. So if this sparsity graph is Chordal, then you can, from what we saw last lecture, show that this intersection graph has a spanning tree that has this induced subtree property. So this is the intersection graph for a larger problem. These are these index sets. Then you can find a spanning tree in the intersection graph with this induced subtree property. So all the index sets that contain a given vertex, for example 16, form a subtree. And in algorithms that is sometimes helpful because it means to find the other index sets that share the same element. You only have to look in a tree, you don't have to search for the whole graph. But we already use this in this. And then again, to go back to the main motivation for looking at partial separability, this SDP, Chordal SDP with in the non-symmetric form is an example of a partially separable cone. Because in this case, the cone C that we had was the full positive semi-definite cone in some vectorized format. And then it's completable if different submatrices, principal submatrices in the cone are positive semi-definite. So you have different overlapping matrices that have to be positive semi-definite. So that's an example of partial separability. Okay, so then we're interested in conic optimization problems with these two cones. So that's the partially separable cone. And, according to our definition, this would be the dual of that partially conic LP. And then in decomposition methods for interior point methods or first order methods, a sort of obvious idea to exploit this structure is to introduce splitting variables for each of these subvectors. So each of these is a subvector. These are overlapping subvectors of the same vector x. So we'll introduce new variables for each of these subvectors. And then add constraints to make sure that everything is consistent. So that gives us this formulation. So the xk tildes represents these different subvectors of the same vector x. So each of these now is independent, lies in a different cone ck. This is general notation that we use for the consistency constraints or consensus constraints. It just says that each of these sub-vectors, x tilde, represents a different overlapping sub-vectors from the same vector x. So that means they have to be consistent. So if sub-vectors of x k tilde refer to the same variable in the original variable x, they must have the same value. They're different copies of the same variable. So that's just a simple linear constraint that we just tried as a set or subspace constraint. And then the coefficients in the problem are we call ak tilde, ck tilde, and there are infinitely many ways in general to get something equivalent. Because now we introduce for every variable in x, we may have multiple copies of x. So if you want to express c transpose x, you can write that as an inner product or a linear function of those copies in many different ways. Because every entry of x may appear in different vectors, x, k, tilde. So you have a choice in coefficients, and it actually can be important to use that. But it's always certainly possible to find matrices ak tilde and ck tilde that are equivalent to the original problem. So we made the problem much larger by introducing all these copies of variables, but we simplified the inequality constraints. They're now independent. And if you apply this to the SDP in this completion formulation, this is known as the click conversion formulation that was proposed by Fukuda and other people in Kujima's group in 2000. And they actually proposed this for SDP for problems where this larger SDP, when we use this decomposition, is easier to solve by interior point methods than the original one. And to see why that might be possible or when it's possible, we have to just look at the main step of an interior point method. So if you're familiar with interior point methods, you know that the main cost per iteration is to solve a large linear equation for the search directions. They're called Schur complement equations, or just the Hessian and Berry method. So if you write this LP after conversion in this way, and then in interior point method, you would have to represent these equality consensus or consistency constraints by equality constraints. So here we write this in this form, in matrix form. So then in general, the Schur complement system that you would have to solve would look like this after some steps. So you have a large system of equations that you have to solve. HK here could actually have different values depending on the method you use. But typically it would be a barrier, the Hessian of a barrier function for each of these cones, CK, or that rule. So it was pointed out when this was proposed, that often this system is of course much larger than what you would have if you looked at the Schur complement of the original problem. But for the original problem, it's often dense, certainly for SDP. After conversion, often there is more sparsity in this bigger Schur complement system. And that depends on how you picked the coefficients AK tilde. But they refer to this as correlative sparsity. So correlative sparsity refers to the sparsity pattern of this 1-1 block. And there's a simple rule to actually see what the sparsity is. So you can assume that HK is a small dense matrix. So then a matrix like this will have a 0 in position I and j if equations I and j in this set of equations never involve the same variable xk. So rows I and j of the coefficients ak are never non-zero for the same ak. They're sort of only non-zero for different non-overlapping AKs. If that's the case, if two equations here never involve the same variable xk, then you have a 0 in this position ij. And that's actually much more common than for the SDP before conversion, where you had a single big constraint, especially for the polynomial relaxation problems that they were interested in, and they call that correlative sparsity. And then this system, even though it's much larger than the original problem before using this decomposition may be easier to solve because this first block is sparse. But the problem is, or the limit of this method is that if you apply this to an SDP, then the number of variables you introduce using this decomposition grows very quickly, because each of these xk's is actually a matrix variable that represents a submatrix of the original variable. So the dimension of this problem can increase very quickly. And then the dimension of this second, the other blocks actually increase very rapidly. So just a small example may help. So if you look at sparsity pattern that looks like this, that's the aggregate pattern before. So there's actually 10 diagonal blocks, then 5 dense rows and columns, and that's a chordal sparsity pattern. So the cliques are actually, each time you have a diagonal block plus the rest of that column and row, and then the small block at the end, that's one clique. So there are 10 cliques. If you do the conversion, then you get this aggregate pattern, and now everything is a block diagonal, because these dense rows and columns have disappeared, and instead of diagonal blocks of size 50, now we have diagonal blocks of size 55. So we did this conversion, and then for each block we'll have to add consistency constraints to make sure that this block that's represented several times is consistent. So then the coefficients in the SDP we picked in such a form that the correlative sparsity pattern is block diagonal. So that depends just on how we chose the coefficients. And then this is the sparsity pattern after of this Schur complement system. So the block diagonal correlative sparsity pattern can be seen here. That's the block diagonal pattern for this 1-1 block. And this is for the other 2 blocks that correspond to the added equations that you have to add with all the consistency constraints. So you see it's quite sparse, but even in a small problem like this, you get something that's this will grow very quickly. This is even for a very small amount of overlap between the cliques. And this becomes quickly quite expensive to solve. But it's an interesting approach, because if you compare the Schur complement that you would get if you didn't use this conversion and solve the same problem using a standard interior point method, you would have actually a dense block of this size, because the pattern would be the Schur complement of this in this 2x2 block, which would be dense. So this conversion method, this clique conversion method is actually quite useful, because it allows you to write, instead of solving a small dense system, a smaller dense system of this size, you solve a larger sparse system. But the limit is that the size of the system grows very quickly, and at some point it becomes practical. So what we did in this paper is to try to do something similar, but with first order methods or splitting methods. So instead of solving this as by an interior point method, we solve the same problem with a splitting method. And then it's useful to look at this converted problem as a problem of minimizing a convex function f of these variables x tilde, subject to a subspace constraint, just the consistency equations. And then this objective function f is just the objective in the problem plus all the constraints. So it's a function that's equal to the objective if the other constraints are satisfied, and plus infinity otherwise. So it's the objective plus an indicator function for this part of the equations. But the domain of f does not include the consistency constraint. That's the important thing. It's only this part of the matrix. So we can try to solve this using a first order method, and a popular choice is Douglas-Ratchford method, which is known under different names. If you apply it to the Douglas-Ratchford method, is actually in general a method for solving a sum of 2 convex functions that each have a simple proximal operator that are defined. So here, if you write this as a sum, you would add f of x is your first function, and then the indicator function of this subspace is the second function. So the second function is 0 if x is in V, and plus infinity if it's outside V. So that's a convex function. And if you apply it to a problem like this, Douglas-Ratchford method, it's also known as Spingarn's method of partial inverses. That's a method from the 1980s, and the equivalence was shown by Eckstein and Martzikas. And the Douglas-Ratchford method itself has a long history, so it was first proposed as a method for linear equations in the 1950s by Douglas and Ratchford. And then Dion and Mercier showed or extended it to monotone operators, which is actually more general than solving the sum of convex problems in the 70s. It's still known as the Douglas-Ratchford method, but it's actually much more general than the original Douglas-Ratchford method for linear equations. So it's a very simple iteration in 3 steps. We have 3 sets of variables. So x tilde is the one that we're interested in. And then I have 2 other sequences of variables. The third step is a simple combination of the 3. The second step is projection on this subspace of consistency constraints. So in our case, that's a very cheap step, because this consistency constraints was just expressing the fact that these variables, x tilde, are different overlapping subvectors of the same larger vector x. And to project a vector, a set of vectors that are not in the subspace on this, you just have to take the average. For each variable that appears multiple times in these subvectors, we take the average and replace each of these multiple copies by their average, and that's projection on the subspace. So that's a very cheap operation. And in addition, you have this Chordal structure in the sparsity graph. You can actually use this induced subtree property to actually even do it more efficiently, because these multiple copies of the same variable all appear in a tree in this intersection graph. But that's not important. So it's a very simple projection. So the first step is the proximal operator of this function f, defined like this. And the proximal operator in general is defined as a solution of this. So for a general convex function, closed convex function f, the prox operator is defined as the minimizer of an optimization problem with f of x as objective, augmented with the Euclidean squared distance between x hat and z. So that's to find the prox operator at z. You have to solve this problem, and the solution x hat is called the value of the proximal operator of z. So for many simple functions, f that's has a closed form expression, for example, the one norm is the most famous one, and you get the soft thresholding operation. If f is an indicator function, and this is just Euclidean projection on the set. But here we'll use it, actually we'll evaluate these proximal operators numerically. So this is our function f. For general A and cons, or general AK, it doesn't have a simple expression, but it may still be much easier to solve numerically than the original SDP. So that's what we'll do. So we'll have to then look at the cost of solving or computing the proximal operator for that cost function. So in general, that's a quadratic optimization problem, because we added this quadratic term in the objective. And the important thing is that the Schur complement system that we have to look at to determine how efficiently we can solve this has this form. So it has the matrices AK tilde. Then instead of where we had H inverse before, H was the Hessian of one of the barrier functions, now we have HK plus an identity matrix that comes from the Hessian of this. But still, in general, this would be a simple matrix, the Hessian of the barrier function plus identity. And so that's the equation. And the important thing is this, the sparsity of this system has what we call the correlative sparsity pattern of the original. Because here we removed all the consistency constraints that coupled everything. So this, in many applications, will be very sparse, even though the original SDP was very dense. And it may even be block diagonal. And if it's block diagonal, then you can actually solve or compute or evaluate this proximal operator by solving L, if L is the number, independent proximal operator systems, and do that in parallel. So then it's really decomposition. If you can manage to do this, split up this proximal evaluation in L independent problems. But even if it's not block diagonal, but just sparse, it's still interesting to do this because it has this correlative sparsity. So for SDP, actually evaluating this is a little more complicated. So we had to write a special purpose solver to evaluate these proximal operators for SDP. Because if you compare with CVX, this is the cost of evaluating a proximal operator for actually a single block CK, a matrix of order P. For CVX, that's the top curve, and then some other solvers, SDPT3, with different formulations, called directly instead of via CVX. So there's a big gap between the special purpose solver and the general purpose solvers. And the main reason is in, first of all, handling this quadratic term in the objective. And then also you have to, for SDP, this becomes more complicated. You have to do something, use a special trick to reduce the cost of this operation. But the cost of solving is, and this is important because if we use this Douglas-Ratchford method, then that's only, and evaluate the proximal operators numerically, then it only is feasible if you can do this sufficiently fast, much faster than the full curve. So here it's a factor of 100 faster than prox operator by just evaluating, by just calling CVX to solve this problem. So without this special purpose implementation, it would certainly be infeasible because every iteration would be 100 times more expensive. So I'll skip this. So from the Douglas-Ratchford iteration, you can actually get stopping conditions and residuals for the quite easily. This is an example of SDP with a graph structure, just to show you the convergence. So here we looked at an Euclidean distance matrix completion problem. So the Dij is a given approximate Euclidean distance matrix graph, or entries in distance matrix. So Dij is an estimate or a measurement of the distance between, the square distance between points I and j in the graph. And the graph is given by W. And then you want to find a true Euclidean distance matrix that approximates those measured values as closely as possible. So you can set it up as this problem. X is a variable, and X was the gram matrix in the EDM formulation we discussed yesterday. And X has to be, you don't need all the entries in X as variables, but only entries in a Chordal embedding of the original graph. And that's E. And then the constraints on X is that X has to be positive semidefinite completable. So we took a graph like this, and this is the type of convergence you get for this Douglas-Ratchford method, where at each iteration you evaluate a prox operator. In this case, the prox operators were actually decomposable. So you had a block diagonal, or decoupled prox operator. For each clique in the graph, you had an independent prox operator, which made this very efficient. And this is a typical convergence you get. You see you need quite a few iterations, and the accuracy is not great. So you get like 0.1% or 10 to the minus 4, but that's only very good for these methods. So they don't converge very quickly, but initially you get a good decrease in the accuracy, in the error, and you can reach maybe 0.1% realistically. But they don't, certainly don't reach the same accuracy as infinite point methods. So maybe we can skip this. This is a larger experiment to compare the solution time of this decomposition method via Douglas-Ratchford with an interior point method. So we took an SDP with a block arrow structure, so that's a Chordal pattern. But in addition, we made it almost separable. So each of these terms, each of these sums involves different variables yi. So you have nu1, nu2, these are independent sets of variables. So it's almost decoupled, except that all variables appear in this last block. All variables y in this dual SDP formulation appear in this block. So otherwise it would be completely decoupled. And then we have different dimensions in the problem, so the number of clicks will be L, D is the size of the block, so we take that fixed to be 20. W is the arrow width, so the dimension of this last block. So we'll vary the number of blocks and W. And then the coefficients AI here are chosen so that after conversion we have this correlative sparsity pattern. And it's actually a diagram. So the prox computation didn't do it, but the prox computation in principle would be completely decomposable. And these are some results compared with SDP3. With so the unconverted Sidomian SDP3, unconverted and converted. Unconverted means the original problem. Converted is the converted problem but solved via material point method. So for L100, the number of clicks is 100, and as a function of arrow width, we see the conversion method, the green curves, initially is a very good solution. For a small amount of overlap, for a small W, this conversion method works very well. It's much faster than an interior point method or the splitting method the interior point method before conversion or the splitting method. And that's because the extra variables you introduce is small, because it's only, you have a small amount of overlap in these cliques, so you only need a small number of extra variables. So the extra cost is small, but it increases rapidly with W. And after a while it becomes actually slower than the unconverted rate. And the gap, so you see that for the splitting method here for these problem sizes was actually slightly more efficient, but of course also much less accurate than the interior point method. And the gap between these two increases between the blue and red one increases as L increases. So as L increases, the size of the problem increases very quickly, and in the this is as a function of L for fixed W, and then for sufficiently large problems, this first order or the splitting method becomes feasible. And it would be much more interesting if you really had evaluated proximal operators using the property that they're decoupled, because then you could ideally reduce this by a factor of 100 or a factor L if you have L. So that's it for this part. So I'll skip the last part of the lecture. I'll include the slides in the PDF. It's another application of this conversion method to relaxations. So I think many of you are familiar with positive semi-definite relaxations. And you can also use this conversion method to, so it's actually it's related to the previous part. In the previous part we had the conversion method. We introduced all these auxiliary splitting variables, and you had to add consistency constraints, and the difficulty was in dealing with the large size of the consistency constraints. Here you could also use that in relaxations, because if you drop some of the consistency constraints, then you still get a weaker relaxation than the original one, but they may be cheaper to evaluate because you may need SDP easier to solve. So that's the point of this example. So actually to finish, this is the main point of the two lectures. So we looked at Chordal sparsity in semi-definite optimization. So for our purposes, Chordal sparsity was interesting because the basic property is that Chordal sparsity allows a zero-fill Cholesky factorization, and that's a very practical and useful factorization of Chordal patterns. If a pattern is not sparse, you can often embed it quite efficiently in a Chordal sparsity pattern by doing a symbolic factorization or a triangularization. And then we looked at two sparse matrix cones, the positive semi-definite and positive semi-definite completable cone. Chordal structure is interesting because it allows us to evaluate the barrier functions and derivatives efficiently and use that in an interior point method. And it's also another property of these Chordal sparse matrix cones is that we have these interesting decompositions. So we can express these cones as a sum or an intersection of very simple cones. And that's very useful for decomposition purposes. And then we looked at 2 of these 3 applications. Thank you.
I have a question for you. The first one is for directed graphs. Does it make any sense to provide the original formal graphs for directed?
There is a connection, but I don't know exactly how it is.
But at least it makes some sense, right?
It does make some sense. And also with an ordering, you get sort of a special sort of directed graphs, or a subset of directed graphs that can also be ordered using a model. So in graphical modeling and machine learning, they do often work with directed graphs.
Yes.
But I don't know the details of how it's related to the graphs.
The second question, can you say a little more about the application for power systems that you
Okay.
mentioned again?
So this is a general idea of an SDP relaxation. If you have a quadratic problem with quadratic inequalities and constraints, then SDP is important because there's this relaxation. So you express it as linear in a matrix variable y that is equal to XX transpose. If it's equal to XX transpose, it's this, and then you relax it. So that's one. So you get an SDP.
Sorry, do you assume a positive difference?
No, so this is general non-convex quadratic. Yeah. We could have, just it should have had a non-convex.
Mm-hmm.
So you write everything as linear constraints in a matrix variable XX transpose. So if you have equality here, it's exactly equivalent. So this is a very difficult constraint, and then you drop the equality and replace it by inequality. So that's the standard SDP relaxation. So in problems with graph structure, as in this power flow problem, the coefficients in the relaxation will inherit some of this graph structure. So suppose this comes from some SDP relaxation with some sparsity structure and coefficients. We use this conversion method or decomposition method, and these would be all the consistency constraints. That say that for all these overlapping submatrices, the different copies must agree where they overlap. So if this is a relaxation of some problem, and we drop some of the constraints, then you get a cheaper relaxation. Actually, I should probably have written maximization here. So you get, if it's a lower bound, you would, so you get a cheaper relaxation if you drop some of the constraints. So you relax it even further. But you remove some of the complexity of solving these relaxations, because it's these overlap constraints that make it very expensive. So the question is, how well does that work in practice? It's just a simple heuristic. So in a classical power flow problem is an actual QCQP, where the quadratic equations come from power balance equations. The main variable is a complex vector V of voltages, and you get sort of different quadratic, it's actually non-convex QCQP. And you can relax it if you take that voltage vector and replace VV, the conjugate transpose of V, this matrix X, as your variable.
So this is a load balancing problem.
Yeah. So you have some, at each node, this would be the power generated at that node, this is the demand, and this is the power injected. But they are complex powers, so these are this matrix Y is the admittance of the power network, so it has a sparsity of the network. And then after relaxation, you get this structure, and then we can use this. So this actually is Martin's work in this paper. This is some test problems with different sizes of n would be the number of buses, is the size of the network. And then this is a table of the size of these relaxations. So this is the original relaxation, which we call the unconverted problem. So the full standard SDP relaxation. This is if you apply conversion to this problem, and these are factors, so this means 3 times this number of equality constraints. So if you do the full conversion of the original SDP, you get 3 times this number of equality constraints. This is another conversion where you merge some of these cliques so you get slightly more efficient. And these are these weaker conversions where you just take for all these overlap constraints, you only keep a certain diagonal of a certain band of the overlap constraints. And this is the half bandwidth of the constraints you keep. So these are much cheaper, they're almost as small as the original unconverted problem, and they're much easier to solve. Right? And then this is actually I should put the cheaper, so this is computation time to solve these by a standard SDP solver. So this becomes very expensive very quickly, and then these cheaper relaxations are actually quite cheap compared to the other formulations, but they're also weaker. And then this table and the last one explain how well they work. So here we look at the eigenvalue ratio. So these relaxations, if the solution is rank 1, then it's a exact solution. So you can look at the ratio of the first and the second eigenvalue as an indication of how exact your relaxation is. So in the first case, where actually the full relaxation was exact, because this is basically a rank 1 matrix. After taking half bandwidth 3 or 2, we have also full relaxation. So this approximate relaxation was actually also exact. And then for other problems, it actually compares quite well with the result of the converted problems. You get the same conclusion if you look at the objective values of the lower bounds. This is the ratio of the bounds of the relaxation to the full standard SDP. And this is a computation. So the conclusion is, by doing this, you get cheaper relaxations that often seem, at least in these examples, to work quite well, and but they're weaker than the full SDP relaxation.
But some of the matrices are now complex. Is that right? While in the original SDP problem,
They were also complex.
Oh, they were also complex.
So this actually also is SDP.
Okay.
Or everything was actually complex.
Okay. Thanks.
Okay, other questions? You know, I have, maybe it's not question, but comment. So the tendency in optimization, now we proceed from large problems to very large or huge problems, and in these problems, interior point methods are not applicable, even if we tailor them by the sparse pattern techniques and so on. So the main interest is in first order, some simple methods, successive projections or something like that. Well, the last part of your lecture was exactly about that, about splitting method, but also I guess that these ideas you presented about this structure, it can be very helpful also for the simple methods, not only for interior point methods. So it is of interest to develop how it works in successive projections, gradient methods, and so on.
Yeah, that's a very good thing. We're actually looking at projecting on these cones by using the decomposition results.
Okay, no more questions? Okay, so